Good morning. In this oral spot, I will present our work learning unbiased representations via mutual information backpropagation. Data collection is a hard problem. It is indeed difficult to collect data with categories seen under all possible distributions. There may be a significant discrepancy between the distribution of the training data and that of test data. For example, we may want to train a self-driving car system using mostly daylight scene images, but having our model to generalize also during nighttime. There may be also spurious correlations between the distribution and the task labels. For example, when distinguishing cats from dogs, we could have most cats to be dark colored, while most dogs to be bright colored. Data representations learned from such data may perform poorly on the test data. The problem of dataset bias can be introduced with the following example. We are given a dataset of colored shapes and we want our model to learn a shape classifier. Our dataset is biased towards color, namely, color appears to be a sensible decision rule to distinguish the two classes on the training set. If the model learns color as a feature for classification, when it comes to deploy our trained model, we may erroneously mislabel some samples just because we haven't observed all possible combination plus color at training time. Among the different attributes which are predictive for the task, we only want to learn those which are general and varied across different distributions. By removing unwanted information, we are able to generalize. Removing information from the data representation has been explored in the literature for different goals. Removing domain information allows the model to better generalize on a target domain, which can be available at training time as in domain adaptation, or not known a priori as in domain generalization. Another branch of application is that of removing protected or sensitive information as in the context of algorithmic fairness or data anonymization. One popular approach to tackle the problem is to learn features which are imposed to be invariant to the bias attribute. Another approach involves training set resampling to better exploit the training samples which are less affected by bias. Another method employs robust optimization and considers the worst-case loss over the potential test distribution. Our method falls into the category of generalization through invariance. We will discuss more in detail this approach and the existing methods. We are giving a training set with input data X, task label Y, and bias annotation C. We split the learning pipeline in a feature extractor G, which produces a representation Z and a classifier F that predicts Y from Z. The parameters of G and F are learned by backpropagating the gradients of the task loss function, usually a cross-entropy for multi-class problems. We aim at achieving statistical independence of Z from the bias attribute C while solving the task. There are different measures of independence in the literature. Mutual information in deep learning has gained much attention in the past years for its capability of accounting for nonlinear relationships among random variables. If we can guarantee that the data representation Z does not contain any information about C, in other words, if they are independent, then the prediction of a classifier based on feature Z do not consider the bias attribute C. Mutual information is a measurement for statistical independence, which can account for non-linear relationship between random variables. Therefore, the optimization problem we want to solve can be formulated as finding the parameters theta and psi that minimizes the cost function, plus the constraint of having mutual information between features and bias attribute equal to 0. This can be rewritten in a single objective using a Lagrangian multiplier lambda that multiplies the second term of the overall cost function. mutual information as an objective is not tractable, as it requires to know explicitly the probability density functions. We briefly review the existing methods that solve the same objective with different approximations before introducing our way to optimize it. One way to optimize the objective is by using a variational inference approach to approximate the intractable distributions. In his work, Moyer and colleagues show that compressing and reconstructing an input sample can achieve invariance to a specific attribute in the latent vector. If the bottleneck is narrow enough, the encoder removes the attribute because such information is then provided to the decoder as a conditional vector. Although theoretically principled, one drawback of this kind of approaches is the scalability. In fact, one needs to train one encoder and one conditional decoder, which can be difficult for large-scale problems. Another family of methods is that of adversarial approaches, which are shown to solve an approximation of the objective before introduced. In adversarial methods, one tries to predict the bias attribute from the data representation Z with an additional module H. One wants this module to achieve random chance when predicting C. This would mean that the feature Z do not contain any information about the bias that can be used by the classifier to predict it. To achieve this, one popular approach is to employ gradient reversal layer when training the classifier. In such way, the optimization with respect to the module H goes in the opposite direction of the gradients. At the end of training, the encoder G of theta is optimized to perform the classification task and not to perform the bias prediction. One drawback of these approaches is how to balance the trade-off between learning the task and unlearning the bias. We now discuss how we solve the problem of learning invariant representations not relying on variational inference nor adversarial methods. We rely on a recent discovered mutual information estimator that is parameterized by a neural network, hence it is fully differentiable. The mutual information neural estimator relies on the Donsker-Varadhan representation, which provides a lower bound for the exact mutual information. The estimation is given by the superior of the formula, where we look for all the functions with real values for which the two expectations are finite. One expectation is taken from the joint probability, while the other from the product of the two marginal. In the paper, the authors suggested to use a neural network to approximate T. Using a neural network, the lower bound becomes parameterized by phi. We can rewrite the previous formula as a loss function, LNE, which can be maximized in order to find the superior. The estimation then becomes the maximum of LNE over parameters phi. At training time, the product of the marginal is simulated by shuffling one of the two mini-batches. We indicate these with the dice in the figure. Our method consists in a feature extractor G parameterized by theta, whose features are fed to a logit layer F that produces prediction with respect to the task. The same features are fed to the mutual information neural estimator. The bias attribute label is fed to the estimator as well. The optimization problem is to minimize the task loss with respect to the parameters theta and psi, and maximize with respect to phi the parametric lower bound LNE. Please note that the estimation of the mutual information depends on the feature vector Z that is produced by the encoder F. Hence, the estimated mutual information depends on theta. We exploit this fact to produce gradients of LNE with respect to theta, which force the feature extractor to seek for representations Z that are invariant with respect to C. The algorithm can be summarized as follows. There are two nested optimizations. One is responsible for updating the parameters of mutual information neural estimator. The other acts on the feature extractor and the logit layer. It is important to note that we need to keep MI constantly updated, since every change in the feature extractor produces a representation whose statistical dependence is different with respect to its previous state. Hence, the need for updating several times the neural estimator. As expected, we observed that the better we estimate the mutual information, the more accurately we are able to remove the bias attribute information from Z. In practice, it helps having large batches of trained samples, or, when this is not feasible, to accumulate gradients. Also, more iterations in the inner loop provide a better estimate. We now discuss the experiments we conducted. We evaluated our method on the MNIST dataset with color bias. Each sample has a color that is sampled from a Gaussian. At training time, all digits from the same class have the same mean color. This means that color is a predictive feature for the class at training time. Differently, at test time, all classes can assume different colors. Therefore, a model that uses color as a predictive factor at test time will perform poorly. We explicitly tell the model not to learn the color. We compare test accuracies on different methods. We firstly observe how having a higher sigma means to have less severe bias on the dataset, since class colors are more spread out. The baseline is a vanilla training from data without any additional constraint about invariance. We observe how our method outperforms others on all the different splits. We show how the choice of lambda influences the amount of mutual information between bias and features, the training and the test accuracy. When we set lambda equal to 0, we perform the standard empirical risk minimization, hence there is no invariance and therefore no generalization. We observe that setting a higher lambda, we get less amount of mutual information. Such increased invariance is also reflected on how much the model generalizes on the test set. Higher lambda means also that the model struggles more to fit the training data, because of the weight that the mutual information constraint has in the overall loss function. So, when choosing lambda, we pick the highest value for which the model is able to fit the training data. This means that we try to minimize the mutual information as much as possible. This hyperparameter choice strategy does not require any validation data to tune lambda. A more realistic dataset is IMDB with photos of faces of celebrities. Here, the task is to recognize the gender. The bias is represented by the age. We have two different splits. In one, the training data is made of young women and old men. The other has the opposite scenario, old women and young men. We encode age as a one-hot vector as in previous work and remove it from the data representation. In the results, we observe how our method achieves good results even on more realistic data. It is worth to note how training on one split and testing on the other is much more challenging than testing on the neutral test set. It is important to note that separating age and gender seems much more complex than separating shapes and color. We also tested our method for algorithmic fairness. The problem is to remove sensitive information from the data representation in order not to rely on such protected attributes when predicting. The goal is to avoid to discriminate minorities that can be underrepresented in the training data and therefore can lead the machine learning model to be biased as well. We tested our method on two popular benchmarks from the fairness literature that are binary classification problems. On the German dataset, one has several information about bank customers and has to predict whether one customer is reliable or not. We don't want to rely on age. Adult has income data about US citizens and one has to predict whether the annual salary of a person is above a certain threshold or not. The protected attribute here is the gender. It is important to stress that here removing the protected attribute does not necessarily imply a better generalization. Producing fair data representation is done only for the sake of avoiding discrimination. We used equal opportunity as metric to evaluate how much fair is the data representation. Equal opportunity measures the difference between true positive rates for protected and non-protected samples. Having lower EO means having a more fair representation. In our experiments, we measured test accuracy and equal opportunity as performance metrics. We compared with existing methods for algorithmic fairness from the literature. We can achieve a good test accuracy while keeping low equal opportunity in both benchmarks. In the chart below, we show how increasing lambda significantly reduces equal opportunity, whereas the test accuracy is only slightly affected. This experiment proves that our method can be used effectively for algorithmic fairness. Summing up, we developed a method to remove unwanted, harmful information from data representation. We hypothesize to know the specific attribute we want to remove. We leverage a neural network-based estimator for the mutual information, so that we can effectively optimize the parameters of the feature extractor. We also address the problem of hyperparameter tuning, which is often an overlooked issue. We proved the effectiveness of our method on different benchmarks, ranging from computer vision to fairness. We thank you for your attention.